signore. Oh, don't worry about it. I'll get it back. There we go. Thank you so much. All right. So we begin. All right. So this is today. I'm going to do the scalar curvature. What people have discussed with scalar curvature, and so let me just start right away with the. So this is just a review of what the lectures were. So in the first lecture, I did the introduction, and that was the joint work with Stefan. And the lecture 2, I discussed Ambrosio Kirchheim and Federer Fleming. Lecture 3, I did part of the paper with Stefan in more detail. And now I'm going to do scalar curvature, intrinsic flat convergence. So Granoff has a paper in which he has some questions about scalar curvature, and I'll put a quote of his up. And then some results with Dan Lee, with Philippe Lefloc, and with Lan-Xuan Huang and Dan Lee, and also some work with Sajjad Lakhsian, who's been here, but he has some very important phone calls right now, so he's not in the room right now, but you can talk to him about this joint work with him, and also some of Sajjad's work alone. And since it's a lot of papers I'm covering today, I'm doing it on the slides here, but lecture 5 will be a Blackboard talk again and more about techniques. So this is more about applications than techniques. All right, so here's the Granoff questions. He says, well, suppose we consider beta to be a notion of curvature, which could be sectional curvature, Ricci curvature, or scalar curvature. There's two aspects to his question. Given this class, this curvature class, what is the weakest topology or convergence, which he calls T, of beta in the space of Riemannian manifolds, such that the limits, and by the way, he means the measure should be the volume form, the one induced by the volume form, such that the limits of beta positive manifolds are beta positive. He uses positive for non-negative. And what are singular beta positive metric spaces? What are the limit spaces that are obtained? And so he points out that when it's sectional curvature, this is completely resolved. It's Gromov-Hausdorff convergence, and it's Alexandrov spaces. And what he means by this is in the sectional curvature case, by the Toponogov comparison theorem, there's a beautiful triangle comparison theorem that only has to do with lengths. And so that notion, a synthetic notion of non-negative sectional curvature can be captured completely by the behavior of lengths on triangles. That will carry through on Gromov-Hausdorff convergence because the distances converge, geodesics converge, and so you have that same property holding on the limit space. Alexandrov spaces are defined to be spaces that have those kind of triangle properties. So it worked perfectly, you could say. And the Ricci curvature case, he writes, the general theory, albeit not fully established, is well underway for both A and B. And I would say that the course we have here this whole week has been discussing the issues of what are the singular spaces with Ricci curvature. Gromov-Hausdorff convergence was not enough. If you have, say, non-negative Ricci curvature, Gromov did prove that a subsequence converges to a limit space, but the limit space didn't have many properties of Ricci curvature at all that was known for a long time until they decided to add measured Gromov-Hausdorff convergence. And so it became crucial not to use just Gromov-Hausdorff convergence, but measured Gromov convergence. We can dump Hausdorff if we wish. And sorry, Hausdorff, it's your institute. And then you have the CD or the RCDs, and you get more and more Ricci type properties. And then comes scalar curvature. And he says some possibilities are suggested by intrinsic flat convergence. And in his paper, he discussed all the sort of properties of scalar curvature that he would kind of like to see holding, but have not yet been proven as holding under sort of any situations that have arisen. So this paper is really very speculative. It's a speculative paper. So let me just talk a little bit about scalar curvature with Ricci curvature, just to compare with the course you've been seeing here. So Gigli has talked a lot about, so you have the measure doubling, right? So the measure doubling aspect of Ricci curvature is a nice sort of global effect of Ricci curvature, but then it doesn't give you things like splitting. So splitting, you needed the Bachner formula. With scalar curvature, you don't have a nice measure doubling. There's two major approaches people use for scalar curvature. One is the Shane-Yao type approach. You study minimal surfaces in the spaces. Stable minimal surfaces have certain properties, but they have to be smooth. And so a lot of the Riemannian results are in dimensions below 7, where the hypersurfaces will be smooth. So they don't even have the Riemannian results in high dimensions. And then the other approach is to use spinor bundles over the space, which gives you something like a Bachner formula with spinors. And then that works in all dimensions as long as it's spin, which is stronger than being oriented. Spin is a pretty strong condition. So those are the two classes of spaces. So you might say non-negative scalar curvature isn't even completely understood on Riemannian geometry yet. And then he's suggesting that you should understand it in the non-Riemannian setting. All right, so the original set of examples of manifolds non-negative scalar curvature that Ilmanen, who is a major player in the world of non-negative scalar curvature on Riemannian manifolds, was suggested as this example in 3 dimensions. No one's really interested in 2 dimensions because that's going to agree with the sectional, right? So it's 3 dimensions and up. This sequence of 3-dimensional spheres he was hoping would convert to a sphere, which has nice non-negative scalar curvature, and so that things should work out in a kind of continuous way. And the intrinsic flat convergence had worked well to describe this. Smooth and Gromov-Hausdorff don't. So that's why, in some sense, intrinsic flat convergence is the candidate convergence to try to study, to at least have a compactness theorem. So it converges in intrinsic flat sense. I discussed this on the first day. And so the question becomes, what properties of manifolds of non-negative scalar curvature can one hope to preserve under intrinsic flat convergence? What are the properties? You at least now have limits, because the Wenger compactness theorem only requires volume bounds, not any curvature bounds. So you have a limit. When is the limit not 0? When is the limit not canceling? And what kind of properties the limit space have? So the idea of all the papers that I'll be talking about today, the approach is to look at space-like general relativity, which gives a certain amount of intuition for non-negative scalar curvature. And the main thing that everyone worries about when they look at space-like general relativity is the possibility of closed interior minimal surfaces. So those are, let's just picture 3 dimensions for the whole day. If you're in 3 dimensions and you have a neck, there's a 2-dimensional surface that's minimal inside that neck somewhere. And somehow, that's a closed interior minimal surface that would be nice and smooth in a Riemannian manifold. This sort of thing causes all sorts of problems in general relativity. It's a black hole, okay? And they usually cut the spaces, and they study only one side. So they say, oh, they call it a horizon, right? And they say, oh, let's look at the universe only on one connected component. We cut all these necks off. We look at one side, and now it's a manifold with boundary type of question. When the boundaries are minimal, so h, the mean curvature is 0, and they're usually stable minimal, which gives you a little more facts. And then they study just the one side. So that's the same idea that we will use here. That's a standard technique from space-like general relativity, and it will help. In these pictures here, there's no, the wells are going like this, so they don't cause any minimal surfaces. But if it opened up again, you could have a lot of nightmares happening without even like a nice flat limit. It would. Remember those pictures from the first day where you could have a tube and the flat limit broke into 2 pieces? So that is happening because the interior minimal surfaces are forming. So we want to cut and only look on one side. All right, so let me just show you some classic Riemannian geometry. Let's stick to 3 dimensions to make it nice. You have non-negative scalar curvature. The famous positive mass theorem, Rashane and Yau, says if your ADM mass, okay, you have asymptotically flat. That means that outside some compact set, the metric tensor is approaching Euclidean metric tensor, and it's approaching fast enough. I don't want to say exactly how fast. They give the precise speed it has to get there. The idea is this is a single solar system or a single planet all alone, and eventually it's getting pretty flat out there, and this is the well of the space-like manifold. And the idea is to show that this Arnowitz-Dissner ADM, let me just say ADM. The ADM mass is a notion of mass that has nothing to do with mass of currents. It's the mass of the space. So if you have a black hole, there's a Schwarzschild metric. It's a vacuum black hole, the Schwarzschild metric, and the mass of the black hole, the radius of the black hole is twice the mass, and the way the metric decays at infinity is the ADM mass records the exact same mass. So when you say you're asymptotically flat, your ADM mass is saying how close you are to the Schwarzschild. Yes, that's their proof. implies, okay, so it's actually positive. So you have an asymptotically flat manifold, non-negative scalar, and this asymptotic flatness, the speed at which it decays is recorded in this ADM mass. And the ADM mass is proven to be non-negative. And if it's 0, it has to be Euclidean space. So this is the key rigidity theorem of non-negative scalar. Yeah. No, it could come out to be a negative value. It's like the order of decay. There are black holes that have negative mass, theoretically, never found. and you could write out the formula for a black hole with negative mass. Yeah. That's not the asymptotic flatness is not telling you that the mass is positive or negative. The mass is like a term, which comes from, it's an integral around large spheres of how the Gij tensor has a flux derivative. And it's physics. These are physicists who made up the ADM mass. And it's trying to capture the flux of the gravity coming out. And it's integrated over very, very large spheres. The spheres are taken to infinity. And then you get a value for it. That it has a value requires a certain amount of decay. But it is an integration over all directions. So it's not requiring a uniform decay. It can decay faster in some directions than others. That's this ADM mass. It has this horrible formula, Gij, jth derivative minus Gji, ith derivative, kind of subtracted, integrated. There's another formula that's much more geometric I'll give in a little bit. Okay, that ADM mass, major theorem Rashane and Yao was showing that that was non-negative just from being scalar non-negative. And second part of major theorem is that if it's 0, it's isometric to Euclidean space. So it's really absolutely flat if there's no mass in the region of the space, which vindicated physics to some extent. This physical formula was intuitively correct. You would think that space-time should not be bending if there's no mass in there. Okay, so here are some pictures. The top row all have the same ADM mass because you see the dark blue part that's out in infinity is identical. Okay, and the second one, the second row, the ADM mass is smaller because it's decaying faster. So just trying to give you a geometric picture of what ADM mass means. Now these are rotationally symmetric, so it's easier to see it. In fact, what I've drawn here, the dark blue parts of these pictures are exactly Schwarzschild, which means it's vacuum. That means that the scalar curvature is exactly 0, and they're rotationally symmetric. It forces an exact shape there. And it's actually a parabola rotated around its indicatrix, for those of you who like, for some amazing coincidental reason, that's how it comes out when you solve it. And the insides, the light blue parts, I'm leaving the vacuum situation. So they could be, for example, a planet where there is some matter, or a black hole with some dust around it. So when it's a black hole, it has a boundary. That's the horizon that you fall through. That's the ones that are holes. And the ones that are filled in are gravity wells of a planet. And outside the planet, it solves the same vacuum differential equation. So it has the same Schwarzschild metric outside. But they're not assuming it's vacuum eventually. I just drew ones that were, so it would be easier to see. In the first sequence, we look at the possibility of what if the ADM mass goes to 0? What should happen to the manifolds when the ADM mass decreases to 0? So with the rigidity theorems in Ricci curvature, you had the splitting theorem, exactly split. And if there was just a kind of long geodesic that's not all the way line, was almost split. So you'd like to say that if this is almost ADM mass 0, that maybe it should be almost Euclidean space. So here are examples just to explore it. Rotationally symmetric is always interesting to physicists, less interesting to geometers, I know. Okay, but the physicists are happy to study even just rotationally symmetric cases. In the first sequence, you see that it converges in the pointed sense. I made these black points to emphasize the pointed convergence. Converges in the pointed, smooth sense to a flat Euclidean space. If there are black holes in there, it can't converge smoothly to Euclidean space, but it can away from the hole. the hole actually can be shown to get smaller and smaller. So as the ADM mass goes down, you can show this hole is getting smaller. So the hole is getting smaller, so it's just really converging smoothly to Euclidean space, except at that edge of that hole, which gets so small. All right, so that's still converging Granoff-Hausdorff to Euclidean space. This one does not converge in the Granoff-Hausdorff sense to Euclidean space. This one converges in the Granoff-Hausdorff sense to Euclidean space with a line segment attached. In fact, that line segment could be arbitrarily deep and converge in the pointed Granoff-Hausdorff sense to Euclidean space with a line, a one-directional line attached, or a line segment of any length, or Euclidean space. And the last one is wells, not black holes, and the Granoff-Hausdorff limit could have a line segment. So this is showing that Granoff-Hausdorff convergence, even in a rotationally symmetric case, is not the right notion of convergence for this question. Is this the, I think I lost, there it is. All right, so what we did prove, Danley and I proved that in this rotationally symmetric case, if the ADM mass goes to 0, then it converges in the pointed intrinsic flat sense. But the points have to be located in a very special place. So let me see if I can point. The points are located on spheres of constant radius, rotation symmetric spheres of constant radius. If you locate it there on a rotation symmetric sphere of constant radius, then they converge in the pointed intrinsic flat sense to Euclidean space. If you locate the points falling down the wells, it converges in the intrinsic flat sense to the 0 space, because it's collapsing around those wells. So we needed to find the right points. Okay, so this point thing of locating down spheres is basically saying, as long as you avoid falling down the wells or falling into the black holes, you're safe. And that would be easy. Yeah, yeah. Right. Yeah, yeah. So basically, the situation is Euclidean or 0. All right. And the last two columns were proven rigorously what I said out loud about them, that they don't go in the CK or Granoff-Hausdorff sense Euclidean. Open conjecture is that this is true without rotational symmetry. Okay. Now, you might say, wow, that conjecture is really, really a big, big thing. But to be honest, this is a much smaller conjecture than what Granoff is talking about. Okay? We're just trying to get one example of an actual rigidity theorem to work, which is much, much less than saying, what is the general notion of the limit space? Notice also the advantages that we're trying to show the limit is Euclidean space, which is something generally kind of nicer to do, to try to show something's Euclidean, because there's so many different ways to prove something's Euclidean. You know. All right, so we have this conjecture I just said. So what did we do in the rotationally symmetric case to prove it? A rotationally symmetric manifold is foliated by spheres. So you have these spheres, we call them sigma r, and they're going up in the picture, right? And there's this notion called the Hawking mass, which is the radiation of the mass through that sphere, the gravitational radiation through the sphere. But the nice thing with the Hawking mass is it has a geometric description. So it's originally defined by Hawking in a gravitational way, but the description is area of the sphere divided by 16 pi square rooted 1 minus 1 over 16 pi integral of the mean curvature squared. Very nice, geometric, beautifully written. And by the way, Hawking is not the one who realized it had that formula. Okay, that was realized much later. But it was proven that this is the agreements with his formula. And the Hawking mass, as r goes to infinity, converges to the ADM mass, because it was defined originally with radiation, and that's matching the radiation. So you've got this special thing in the rotationally symmetric case is that you have a foliation of the spheres, but in general, you have spheres far enough out that start doing this, and the Hawking mass will increase. But you don't know what happens in the bumpy regions. There's no foliation. So we're using the rotational symmetry to get the foliation. We explicitly estimate the flat distance by putting these guys sitting in E4 and then cutting out the deep well at the center and estimating the regions that we can't control. So what we do is basically the light blue regions are cut off, and we just study the dark blue regions, and we show that the dark blue regions get close to the regions, these annular regions, and then we show that the light blue region's volume goes to 0, and that the inside that we didn't get close to also has volume going to 0. So it's like we only estimate part of it of the sequence of manifolds to behave well. Without rotational symmetry, there could be many, many wells. We'd have to cut out lots of things. Where do we locate our cuts is less clear, and there's no foliation. So let me draw a picture of how bad the wells could be. Suppose you want to make a manifold that's rotationally symmetric with non-negative scalar curvature. You could just take a nice Schwarzschild type thing, and then you can glue it to a sphere that will still have positive scalar. And then you glue it to another Schwarzschild. So this picture here of a sphere and 2 Schwarzschilds glue together to make a bowl of sorts. And this bowl has positive scalar or non-negative scalar. The pink region has constant sectional curvature. The constant sectional curvature piece you can glue wells to. So I can glue a well onto the constant sectional curvature piece, and I can glue as many wells as I wish. So you can make arbitrarily many wells, arbitrarily deep wells, and have no Granoff-Hausdorff converting subsequence. That's how bad the situation could be. And the foliation, this Hawking mass foliation is not happening, although it happens. There's a lot of good spheres. There's nothing happening on those wells. All right, so we need new techniques. All right, so what are techniques for proving flat convergence? You can use the definition and explicit construction of a Z and of one dimension higher, and we did many examples like that in the appendix with Wenger. We have many examples done that way, and the original theorem in the rotation symmetric case with Danley is an explicit construction of a one dimension higher space that we've put them in. Or you can use volume estimates and diffeomorphic subregions, which is developed this joint work with Sajjad, and he also continued in this work. So these are, I'm itemizing them, and then I'll talk more about each one. Or you could apply the flat compactness theorem, like Wenger's compactness theorem, to say there is a limit, and later try to prove the limit's Euclidean space. There's Wenger's compactness theorem. There is a pointed compactness theorem of Lang and Wenger. That's Urs Lang. Leflach and I have a compactness theorem that's related to scalar curvature particularly, but rotationally symmetric. And Raquel Perales has one with Ricci curvature and boundaries also. We do have to worry about boundaries because it's pointed. All right? And then we have to prove the limits debates must be Euclidean space after we get the limit. Or one way to try to show that the limit space is Euclidean is to use an Ascoli theorem. So an Ascoli theorem would say each sequence in the manifold, each manifold in the sequence has a map to Euclidean space, and then get a limit of the maps, and then try to show the limit map is an isometry. So that's an approach to using our Ascoli theorem. So on tomorrow, I will tell you about the Ascoli theorems that exist. And all of these 4 techniques have been applied in various papers. So we used our compactness theorem, Leflach and I. Huang Li and I used Wenger's compactness theorem and our Ascoli theorems. And a paper with Stavrov that's going to appear will be using the Laxian methods to show that we get limits. So these are all being applied in a non-negative scalar already. All right, so this is a review of definition of flat, which we don't need to review because I've showed it to you already. Okay. Yeah. It's unknown. And this is a lot of Gromov speculation. The limit manifold, we do not have a synthetic non-negative scalar on Riemannian manifolds. That's why we go back to the simpler case of, well, this rigidity theorem can be stated. Can we get that? Right. Right. And then to be honest, the positive mass theorem is used very often to prove things about non-negative scalar manifolds locally and blowing up. So getting something about the positive mass theorem is a little like getting an almost splitting. It's like it's one of the key ingredients they have, so let's try to get an almost version of it. Yeah. All right, so this is the review of the definition of intrinsic flat convergence. And the explicit construction would, in general, the explicit construction of Z would be to get one dimension higher and really explicitly depending on the Euclidean space is just very easy to isometrically embed in something, and then the other one would have to depend on the manifold. Okay, so we used explicit constructions. And then in that case, we didn't really have to understand all this theory of Ambrosio-Kirchheim, because usually when you explicitly construct a space, it's a manifold, so you can use differential forms and boundaries. So you don't need so much theoretical stuff. Yeah.
Your conjecture was only equal to two-dimensional?
Actually, Dan and I conjectured it in higher dimensions.
Right.
The ADM mass in higher dimensions may be physically less relevant.
Right.
Also, the positive mass theorem hasn't been proven in all dimensions. Okay, so yeah, I can conjecture that. No, right. I would like to stick to 3 myself because there's certain things that are very nice in 3. Okay. Yeah. Yao and Shane both believe the positive mass theorem should be true in all dimensions. They've said that often. But they have not been able to prove it. And as I said, spin gets it to high dimensions, arbitrarily high dimensions, but it has to be spin, which requires constructing a bundle and understanding limits of bundles, right? So, yeah. I'm going to stick to the more geometric stuff. The Shane-Yao proof of the positive mass theorem in 3 dimensions has a minimal surface as a key step. A minimal surface is much easier to picture 3 down to 2. But actually, our rotationally symmetric proof is all dimensions. That was not an issue. Okay, so, and that Hawking mass increasing, all dimensions, yeah. Okay, but it's not actually Hawking. I mean, this is extension using that mean curvature term, yeah. All right, okay, so let me tell you this technique using volume estimates and diffeomorphic subregions. So this is the joint work with Sajjad. What you do is you have 2 oriented manifolds, and you want to estimate how far apart are they in this intrinsic flat sense. And our theorem says that as long as there's 2 big regions that look kind of the same that are diffeomorphic, so U1 and U2 are diffeomorphic, but they could have spikes on one of them and not on the other, right? Then all you need to estimate here is the volume of the part outside, the nice part, plus this constant times the volume of the boundary of the nice part, plus a constant times the volume of the nice part. And the constant is a length that depends explicitly on the change in the metric tensors on the nice part, and on terms depending on the distances on the nice part. This constant goes to 0 if the nice parts they're converging smoothly to each other. Whoa, I just went back, right? So if the U1 and U2 are arbitrarily close together in a smooth way, then the flat distance between M1 and M2 will have the C going to 0. And then the key thing that's left is the volume of the uncontrolled part. That's very useful because what you do is you have a sequence of manifolds, you find U's that are well behaved, that have smooth convergence on the U's, and you have to estimate the volumes of the part where it's not smooth. Okay, so here's the proof. What you do is you take your first manifold, here's, say, your one manifold, and here's your other manifold. And so this manifold has some strange topology away from the U that's nice. This one has different topology. He has some sticks out. We're not assuming U is connected. You could have 2 parts. So we have the U is 2 pieces that look almost the same. This piece looks almost the same on this manifold and this one. This piece looks almost the same. And then the regions where they don't look the same, I drew quite different looking. And it was important for any applications that you don't want to require these U's to be connected. You know, if you certainly don't want to restrict yourself. So we have this open set. These nice. We have the sides that are the diffeomorphisms, the 2 sides. And now we have to construct the Z. So what we do is we construct the Z by taking the U that are diffeomorphic and crossing them with intervals that are high enough. That's the solid part of the Z. And then we're going to glue the M1 on top, and we're going to glue the M2 on the bottom. Now, you want the distance from here to here to be the correct distance from M1, so it's distance preserving, which means you have to make it far enough that you can't go down, take a shortcut, and come back up. So that's where you figure out the height here. These heights, these h's and a's and h bars, they're three parts. The h bar comes from the diffeomorphism here. The h bar here comes from this diffeomorphism. The a comes from another term. We explicitly write out what is exactly the value of h bar, a, and this h bar in terms of this and the distances on the US. It's explicit formula so that the c ends up being a plus 2h bar because, okay, what's the flat distance now? We're sitting inside z. What is the flat distance between these two guys? The flat distance is an a plus a volume of an A plus a volume of a B that's one dimension higher that fills them in. So what fills in this guy and this guy? Well, the A part is supposed to make them a cycle. So we subtract this off, we subtract this off, and we subtract this off. They're all part of the A. Once you subtract off these extra pieces as part of the A, now they're the boundary of something. So those extra pieces, that's the volume of A part. So it's the volume of A of the same dimension. So that's the volume of A part. The C, this is also part of the volume of A. Where is that coming from? That's the boundary of this vertical stuff. The boundary of the vertical stuff comes from the boundaries of the U's crossed with the interval. So it's the height times the volume of the boundary of the U's. And then the solid B part that's one dimension higher is the constant times the volume of the U's. Okay? So you get a certain amount of volume from here, a certain amount of volume from there. All right, so that's what I mean by an explicit construction. You actually just make the manifold that's one dimension higher. But you only have to do this explicit construction once if you're in the setting where you actually have the diffeomorphism. We've done the explicit construction. You never need to do it again if you have control over volumes and some diffeomorphisms. Okay, Lexion has used this. So I copied that theorem again. This is his application. Suppose you have a sequence of manifolds. You have a sequence of manifolds with metric tensors, and the GIs converge to G infinity smoothly on M away from a singular set, and that the singular set has Hausdorff n minus 1 dimension 0. Okay, so it could be a pretty big singular set, but it's converging smoothly away from the singular set. We want to apply this theorem, but the U's have to be open here. So you take a connected precompact exhaustion of M with the singular set removed. You assume that the diameter of the exhaustions are uniformly bounded. That's easy. That's just the diameter bound on the whole sequence. The volume of the boundaries has to be bounded above. That's to get this kind of bound for that part. The volume of the M's take away the WJs is less than or equal to VJ. VJ doesn't depend on I, and VJ goes to 0. That's allowing us to control this part. Then you get a flat limit. All right, what's nice about this theorem? An awful lot of partial differential equations on manifolds. You solve the partial differential equation to get the metric tensor, or you're flowing in Ricci flow, your metric tensor is changing, you get smooth convergence away from a singular set. That's standard. And so now you just have to check this. So in fact, Sajjad did in the paper where he proved this, he applied it to study Ricci flow related to singularities, also Calabi-Yau manifolds, sequences of Calabi-Yau manifolds. So this immediately can be applied to situations where the metric tensor is defined with a partial differential equation, which scalar non-negative fits Einstein equation, the GR people. This should be helpful there too. Okay. He is very busy today for emergency reasons, so I apologize. He would be here. Okay. LeFlanc and I use this to study manifolds with non-negative scalar, and also Stavrov and I use it for special cases of manifolds with non-negative scalar to prove the conjecture I mentioned with other conditions. Okay. Now there's the method of applying a flat compactness theorem. So if you want to apply a flat compactness theorem, then you could use, for example, the work with Stefan Wenger. We have the integral current spaces. So you'll get a limit that's an integral current space, but then you have to show that integral current space happens to be a Euclidean space. Okay. Wenger's compactness theorem says you only need a bound on the volume, a bound on the boundary volume, and a diameter bound. You get a subsequence that gets one of these nice limits. And Lang and Wenger have a pointed version of this. The limit spaces in the pointed case are not officially integral current spaces because they have infinite mass. So you had to redefine things a bit. Lang and Wenger did that. So they call them local integral currents, because locally they are. But actually, this isn't a problem when we're talking about getting a limit space that's Euclidean, because Euclidean space is well defined. So Raquel has, just using this theorem, if you have Ricci non-negative and the mean curvature of the boundary is negative, and the volume of the boundary is less than or equal to A naught, and the diameter of the boundary is controlled, then a subsequence converges in the flat sense, because she shows that it has these volume bounds. Okay? The proof uses Laplace comparison theorem that she has to prove in that setting with the boundary and method of barriers. So that's what I was asking about barriers. So I expect something like this would probably also be true if the sequence was not manifolds, but mean curvature. H is the mean curvature. Yeah. Yeah. So she is able to set up the barriers with just a boundary with a nice mean curvature. She has other theorems in the same paper. That's just one of them. The reason I mention this one here is because we were talking about Hawking masses, and the Hawking masses involve mean curvature. So it's important to keep track of what is known about mean curvature. One could apply these sort of things. Of course, non-negative Ricci doesn't allow you to have wells like this. So it's a very different world. Okay, in the paper with LeFloc, we did the rotationally symmetric case again. I know that seems very restricted, but rotationally symmetric is of importance if you're studying a single gravity well. We assumed that the metric tensors were only H1 regular. This is because LeFloc and Madare and a number of other mathematicians he's worked with have been studying the general Einstein's equations with H1 regularity, because they don't need more than H1 regularity to define these Einstein equations in space-time. And then you look at the space-like ones, they'll be H1 regular. And monotone just means that they're opening up instead of having any of these holes, which we don't want to have any minimal surfaces inside. And we assume that, where did it go? No, yes, here. We assume scalar non-negative, Hawking mass of the region less than or equal to H naught. So that's not mean curvature, that's Hawking mass, which depends on mean curvature, okay? The Hawking mass is less than this H naught. The volume of the boundary is exactly A naught. The depth is less than or equal to D naught. Depth is how far down it goes. Like a this is like a diameter condition, but I'm not exactly requiring diameter condition. This condition and this condition are both kind of second differentiable. So we only are H1. So these have to be understood in a generalized sense, okay, with test functions. So in a generalized sense, scalar non-negative, in generalized sense, Hawking mass bounded above can be defined with H1 regular metrics that are rotationally symmetric. This set is flat compact, meaning that the limit space is H1 regular rotationally symmetric also, and has the exact same notion of non-negative scalar and the exact same notion of Hawking mass bounded above. And the Hawking mass turns out to be continuous with respect to flat convergence. So that was pretty surprising. Now I know this is only the rotationally symmetric case, but this was completely unexpected. Somehow it is keeping the Hawking mass under control if the Hawking mass is under control for the whole sequence. In the actual proof, which I don't do the slides and slides and slides of, the scalar non-negative and the Hawking mass are controlling the second derivatives from above and below in a generalized way. And somehow by doing that, the squeezing, the combination gets preserved. If we had only assumed the non-negative scalar and didn't do this, it doesn't get preserved. And if we only did this one and we didn't do the non-negative scalar, it doesn't get preserved. It's the combination that's doing the right thing. So I mean, intuitively, it's like saying Ricci curvature and volume. Like the up and down, you know, the lower, the CD version of Ricci, you know, of things. This is, somehow this is providing the counterbalancing. So this is all work like saying, what intuitively can we try to do, maybe, right? Right, so you can conjecture if this is true more generally. We just didn't.
I don't agree
The Hawking mass increases if it's 0, and the rate of increase can be better if it's positive with a known amount. Okay? So we, just like the Bishop-Gromov volume comparison is much simpler to state with non-negative Ritchie, the increase of the Hawking mass is easier to understand, which is scalar 0. But they do have corresponding, yeah. Now, scalar strictly positive cannot be asymptotically flat. It must close up because the ADM mass, the Hawking mass would increase so fast that it could never reach a constant ADM mass at infinity. Sort of basically the one way to see that. People do study, there is physically important reasons to study scalar greater than -1, or negative n times n minus 1, which is what they say. Okay, that is actually important physically. It has to do with space-like slices of the universe that are asymptotically speed of light. So there are many results in that direction, versions of the positive mass theorem, and they study something called the Bondi mass, which is the version of the ADM mass. But it's asymptotically hyperbolic. So if it's scalar bigger than the -1, it's asymptotically hyperbolic, and there's a different n's Bondi mass. But I have not done that, and I don't think they have all the positivity done yet, even. Okay, so we need more compactness theorems to do this, and especially what would be fun is a compactness theorem of this style without the rotational symmetry, of course, right? Because that would be really exciting, right? Okay, I mean, the Wenger compactness is really beautiful and powerful because it requires so little conditions at all. Now, notice, by the way, this includes that it doesn't cancel. It doesn't disappear. Okay, these guys. And that's because of this fixed area here. That's keeping it open. Okay, so if you want to do this more generally and get rid of rotation symmetric, you still want the boundaries to keep yourself open. You want the boundaries to be nice enough. Which is true. If it's asymptotically flat, the boundaries out there are nice. So that keeps, it's really the boundaries that are keeping you from disappearing. Okay. All right, so then you might say, well, if we're going to take intrinsic flat limits and then try to prove that it's a Euclidean space, you're saying that you want to prove the positive mass theorem for an integral current space. Do you have any hope to prove a positive mass theorem for an integral current space? You've just taken your sequence, you got a limit, you want to show it's Euclidean space. You better show it's non-negative scalar on an integral current space. What does that mean? And to prove the positive mass theorem, you would want minimal surfaces inside that space. That's probably more doable. But the non-negative scalar is not yet understood. And there are examples that are really horrible with Basilio and me that's going to appear. They can show you kind of really how horrible M infinity could be if you allow interior minimal surfaces. If you allow interior minimal surfaces, it's all a nightmare. So somehow this thing that the physicists have been doing to cut off those interior minimal surfaces is probably the right thing to do in the geometric questions as well. LeFloc and Mordari in 2007 have developed generalized notions of curvature for manifolds with H1 metric tensors. And so they have non-negative scalar without rotational symmetry required. What it means. And not what it means for the Hawking mass, what its value should be is a generalized notion. So that doesn't require rotational symmetry. Just our compactness theorem requires the rotational symmetry. And there's the compactness theorem again. It would be nice to prove a Hawking mass compactness theorem without requiring the rotational symmetry. If we do this, then there's a paper by Jauregui who says that the limit space that one would attain would have ADM mass equal to 0, so that you would then have to only prove the positive mass theorem on H1 metric tensors, not, okay? So he already has this, going from Hawking mass to ADM mass. Okay, so can we prove the positive mass theorem? I think this is very, very difficult. The Hawking mass compactness theorem would be much easier than the positive mass theorem on the limit space. Okay. The reason why I'm saying this is very, very difficult is the same reason they haven't proven the positive mass theorem in dimensions above 8. They haven't handled the minimal surface that's not smooth. Okay? So it's the same difficulty. Now, if they solve that, those techniques might be used here, right? Okay. And, you know, we're talking about Fields medalists stuck for 25 years. Okay? All right, okay. Well, this one is like, we just made the conjecture last year, so maybe it's not so bad. Right? Okay. All right, so now suppose we do the Ascoli theorem approach instead. You take your limit, you get an M infinity, and then you want a sequence of functions that go to Euclidean space and show that the limit of the sequence of functions will be an isometry. That seems a little more doable because then you're using the properties of the manifolds on the way there rather than the properties on the limit space. Okay, so let me draw a parallel with the almost splitting theorem, right? You have the splitting, you want to prove the splitting theorem on the limit space. You prove the almost splitting theorem, and you take the limit of the almost splitting theorems and then pull it out. That's one approach. I mean, that's not the approach he did, but that's one approach that you could do. So that's sort of what this is. And our Ascoli theorem would be saying, okay, we're not talking splitting, we're talking a map to Euclidean space. That's why we have a function going all the way to Euclidean space instead of trying to argue with splitting. Okay, so can we find an isometry from the limit space to Euclidean space by taking a limit of nice maps? Okay, the Ascoli theorems that one needed, there's a paper entitled Ascoli theorems for intrinsic flat. That paper has a number of different ones, one of them about isometries. This is the particular one that is useful in this setting. You have a sequence of FIs that go from a manifold to a compact set. Okay, you do a disk in Euclidean space if you want to apply it to Euclidean space. And they're all Lipschitz, and they have a uniform bound on their Lipschitz constant, and the MI is flat converged to M infinity. Then there's a subsequence of the functions such that the F infinity converges, the functions converge to an F infinity with the same Lipschitz constant. Okay, so we have this guy, and then you can start trying to show he is in fact an isometry. If you control these guys enough, close enough to being an isometry, then he would be an isometry. Because when you say functions converge, you mean that if the PIs and MI converge to P infinity and M infinity, Fi of Pi converges to F infinity of P infinity. It's the same as the one for Granoff Hausdorff. So I'll talk about that theorem and how to prove it tomorrow. So we use this version, this approach, to proving the limit space is Euclidean in a paper with Huang Li and S. So what we assume is that the sequence of manifolds have graph embeddings into E4. Okay, so you have manifolds that are, they're over E, you have your R3 in R direction, and it's a graph over R3. And it has the pullback metric from Euclidean space. If it has non-negative scalar and depth, then if the ADM mass goes to 0, then they converge in the intrinsic flat sense to Euclidean free space. This allows multiple wells. It's just a graph over 3 space here. So this is much more general than rotationally symmetric. All right, why are we adding this condition? Well, because it gives us the FIs that are Lipschitz maps. Our Lipschitz maps are exactly these FIs. They're not going into, our K is a cylinder in E4. So we do this for cylindrical regions, cutting it. The FIs themselves are our candidate Lipschitz maps. They're maps from MI to E4 with its Euclidean metrics, so their Lipschitz constant is less than or equal to 1, because there might be shortcuts in the Euclidean space. But we have these FIs, and we know that a subsequence converges. We have scalar greater than 0, depth less than or equal to D naught. What's the first thing we get? The first thing is we have estimates from prior work of Huang and Li, which apply Huang Wu and Lam, which allows us to control the volumes. Once we control the volumes and the depth gives us diameter control, we have Wenger's compactness theorem. There is a limit of these guys. Okay, so we have a limit in M infinity. It's an integral current space. We have our M infinity. We have these FIs, they're all Lipschitz 1, so our Ascoli gets applied, and we have a limit F infinity that takes our integral current space to E4. It's actually can even be shown to be a graph. So now we have a map from our integral current space to 4-dimensional space. All right, but you want to show it's to E3, that it's flattened, right? Okay, so now that's the significant work beyond the Ascoli, where what you do is we show that as I gets higher and higher, it actually goes into a smaller and smaller cylinder in E4. So the image ends up being in an arbitrarily small cylinder, and therefore in a disk. So we get that the image is a disk. And this lip less than or equal to 1, so we have the one side of the isometry, and we just have to force it to the other direction. And we use an isoparametric estimate. We say, well, we know the boundary has to be in the circle, but the mass is lower sigma continuous. So if it had gone in too small, then it wouldn't fit. That fails the isoparametric problem on Euclidean space. So we're forced to have the volume a certain size, but that forces the Lipschitz constant actually to equal 1 everywhere. So we get an isometry. So it's isoparametric. If there was one more line here, I would say the significant work beyond all involves isoparametric question and lower semi-continuity of mass. So it's very geometric. All right, how much time do I have? Oh, maybe 5 more minutes. Okay, so now let's talk about the open questions. So I already proposed a list of approaches to the positive mass stability conjecture. Generally, the attitude is that one should try to prove it with special situations, like that graph case. There are other special cases that are nice, that are listed in the end of our paper. One of those special cases is Huskin and Ilmanen proved the positive mass theorem using the inverse mean curvature flow, which is a generalized flow. Okay? It's defined using level sets of functions. That kind of argument is less regular than the Shay-Niao proof. Okay, so one might try to do that kind of argument on an integral current space. Okay, so that's one of the ones we discussed. So in the last section of this paper, we have a number of open problems broken out and approaches you could use. And the same approaches that were listed there might be used for the Hawking mass compactness theorem. Similar ideas might work in the same special cases listed there. For example, one could try to do the graph case of the Hawking mass compactness theorem. That hasn't been done yet, right? You can also, Gromov, I just said the main thing from the overarching statement in this paper, but he does make some speculations on synthetic properties of scalar. So that's, of course, something people can look at. What are those? Would those get preserved under intrinsic flat? With his speculative synthetic notions. And next lecture, what I'm going to do in detail is try to discuss what you get from this sum. So it's Arzello, Ascoli, and Bolzano-Weierstrass theorems. This is going to include, we know already that there's a convergence of boundaries. So if you have a sequence of manifolds and they converge in the intrinsic flat sense, we know that the boundaries converge. We have semi-continuity of areas and volumes. If they're approaching an infimum, that forces continuity of area volumes, which is already being used for the scalar questions, right? Continuity of the filling volume, I probably won't really have much time to discuss at all. It's just really, really difficult to define filling volumes. There's a notion called slice filling volumes, which is in a paper with Portuguese. He's located, he works with, wow. Okay, he's located in Germany. So you can invite him to give a talk. I'm losing who he's working with. He's a postdoc here. Leipzig, right? Okay. And then this is I'm going to try to do in detail. So these are theorems where you have a sequence of functions. When do you get a limit? When don't you get a limit of the functions? Bolzano-Weierstrass theorems are saying if you have a sequence of points, when does the subsequence converge? We know that intrinsic flat convergence points often disappear. So these theorems are conditions on points that guarantee they won't disappear. Okay, so they're very useful. They've been used in a variety of settings. Then there's semi-continuity of eigenvalues. That's Portuguese. He's proven that. Eigenvalues are Laplacian. And applications to covering spaces and the covering spectra, which is a topological application. So what topological things are consequences of having the intrinsic flat convergence is in joint work with Zera Sinai, who's a postdoc at Cron. All right, that's everything. Thank you. Yes.
This distributional notion of scalar that
Yeah.
you talked about, so there's no hope that this would become valid in the
It depends on the GIJ metric tensor. Yeah. Really, it would be worthwhile to go through Granoff's suggested synthetic properties in that paper and just see which ones have a hope. Have a hope to make sense with the intrinsic flat. A lot of them involve minimal surfaces in the space. In mean curvature and minimal surfaces, which is just a natural thing. With non-negative scalar, it's all about mean curvatures, minimal surfaces, and the nice behaviors of those things inside. So we don't have triangles, and we don't have masses transported, but we have minimal surfaces that do nice things. And mean curvature flow, inverse mean curvature flows, and mean curvature flows might behave well.
And you get these minimizers because you're in intrinsic. I mean, you have these like current spaces.
It seems to me that on a current space, you should be able to define something that's also defined with currents, right? A minimal surface, yeah. Thank you.